An astonishing number of engineering problems have been solved using magnetism. Now, these guys have a lot of fascinating properties, but the one that I find most interesting is their ability to push on each other without actually touching. Let's start with a super basic problem that we all have but we don't think about: switching things on and off. Every electrical device requires a closed loop between the thing being powered and the power source. Switches just provide us a safe place to break the connection or separate the wires between the power source and the thing being powered. I cut one of these guys open for you just so that I could confirm for you that there's a metal tab on the inside, and when you move this switch up and down, you are essentially moving that metal tab up and down, which is allowing you to connect and disconnect the two wires. But this type of setup has some limitations. The wires, as well as the switch, need to be able to handle the full current of whatever items are plugged in on that circuit. What that means is, as the power needs go up, so does the size of the wire and the size of the switch that you need to break the circuit. Now imagine a scenario where you've got an electric motor that's hundreds of yards or meters away from where you want the switch to be located. You're going to need a whole bunch of this really bulky, difficult to work with, difficult to cut, and super expensive cable. Plus, you're going to need the bulky switches. Okay, here's where things get interesting. The switch itself has to be able to handle the full current of whatever's plugged in. But it doesn't actually take that much power to move the switch itself. What if I use an electromagnet to open and close the switch? This doesn't require very much power, so my electromagnet doesn't have to be very strong. Now I have a low-powered circuit that can control a high-powered circuit. Introducing the relay. Relays are electromagnetic switches. Basically, they let low-powered circuits turn on high-powered circuits. Inside your vehicle, there's an electric motor called a starter, which is used to turn over your gas or diesel engine. But that electric motor requires hundreds of amps to get your car started. Imagine having a switch like this on your dashboard. Instead, engineers use relays in order to move the switch and start your vehicle. I've set up a similar thing here with my dust collector. I've got relays inside this cabinet right over here. That's going to allow me to take a 24-volt circuit and turn on a 240-volt circuit. Yes, here in the United States, we have 240 volts as well as 120. All I have to do is turn this relay on. And as you can see, I have a very, very low-powered circuit controlling a high-powered circuit. And because there's very little current flowing through this wire, I can use a much smaller, much cheaper, and much longer wire. Pretty much any time that there's a small circuit board or a computer controlling a high-powered device like your air conditioning unit, there are going to be relays involved. And as I hinted at before, the electromagnet is the foundation of the relay. But what's an electromagnet? When you run electricity through a wire, there's a magnetic field produced around the wire. In fact, that magnetic field has a north and a south pole. To demonstrate this, I'm going to use this compass that I have laying on my workbench here. Now, north is directly behind me, and this wire currently is connected to a circuit that is off. If I turn the power on and apply some voltage, you'll see that the compass needle is starting to turn to align itself with the magnetic field of the wire. That's because that magnet is a whole lot closer than the Earth's magnetic field. When I turn the power off, it goes back to the Earth's magnetic field. It gets even better though. If you take the wire and coil it up all in the same direction, the strength of the magnetic field increases. And if you take a piece of iron and shove it in the middle, that also increases the magnetic field. My plan at this point was to make an electromagnet for you. But as you can see, my dog got a hold of this and really chewed it up. There are a lot of bite marks, and I just don't trust that this wire is safe to use anymore. All is not lost, however, though. I do have a bunch of these little fans that I take out of broken microwaves, and they happen to have a perfect coil right there. This is essentially what we're making. It's got an iron core and a coil of wire wrapped around it nice and tight. And you're going to take this and do exactly that. You can use a steel bolt, but iron would be much better. And you're going to coil it up around the bolt. The only other two things you need to know is that you're going to have to sand off the coating from the ends of the wire, and the coil needs to be continuously in the same direction. The bigger you make that coil, the better. You don't need a whole lot of power for this to work. In fact, I'm just going to use a 9-volt battery for this first demonstration. Now, as you can see, right now, it's not picking up this washer, even though it's made out of steel. But if I touch the ends of the wires, now it's magnetic. And just like a switch, if you disconnect a wire, you lose your magnetism. Bonus question, is this considered a short circuit? Leave me a comment, let me know what you think. Back to science. There's one more variable that we have control over, and that's how much power we put through the circuit. If we increase the amount of current flowing through the wire, we increase the strength of the magnetic field. I can show you that by trying to pick up this larger washer. And it's definitely pulling on it, but not quite strong enough to pick it up. However, I got a power supply sitting right here, so let's hook that up. All right, no power right now, but if I turn this up to, say, about 40 volts, now we've got a way more powerful electromagnet. And that's fully scalable, right? We use electromagnets to pick up cars. Now that we have that foundation on the electromagnet, let's take a look at the relay itself. Here we have a relay, and this is the relay's big brother, the contactor. I say big brother because functionally these guys are pretty much identical. So for the most part, the things that I say about the relay also apply to the contactor and vice versa. And when the differences matter, I'll try to point those out. Despite the fact that they operate on exactly the same principle, you'll see that the contactor is significantly larger than the relay. And that's because contactors, in general, are designed to handle much higher currents. Inside of this box is a coil that is identical to the coil I showed you earlier. Taking a closer look, you can see that this relay also has a coil right here. All right, let's switch to a larger one so that it's easier to see the wires and the coil. Here you can see 4 tabs which are connected to a lever. The lever is actuated by the magnet as well as this spring that's on top. The relay has 2 positions. We have what's called the normal position, which is the one you're looking at now. And then we have the activated position, which is what it looks like when the coil is turned on. Let me connect it up to power real quick and I'll show it to you in action. I have the relay coil wired to this momentary switch. When I push this button, the coil should move from its normal state to the activated state. All right, let me stop kidding around with this. Earlier you saw that there's a whole bunch of screws here on the top. All of those screws correspond to some of these little pins that are sticking out. Power supply is off. I'm going to pull this ice cube portion out. Now, all of these behave exactly the same, so we're just going to take this first one and then you can extrapolate that to the others. We've got this copper strip which comes up and is soldered to this wire, and if you follow that wire around, you can see that it connects right here. What that should tell you is that this pin can be connected to either this one or this one, depending upon the state of the relay, right? When the relay is on, we're connected to this one, and when the relay is off, we're connected to the other pin. The technical term for these pins is normally closed and normally open. Now, I just threw 2 words at you. Normal refers to when the coil is off. That's the normal state. And the activated or opposite state is when the relay is on. One way you might be able to keep this straight in your mind is if you think of a closed circuit as like a series of walls with a door in it. When the door is open, the circuit is broken and electricity can't flow through the wall. When you close the door, electricity can flow. So in this case, our door is normally closed and somebody has to come along and act on the door. In this case, our coil will act on the door and swing that circuit open. This one is now disconnected and the other coil is activated. The same vice versa. This door is normally left open and when you act on the coil, it is closed and electricity can flow. The most important lesson you can learn from this is that this coil can either disconnect a circuit or connect a circuit. Let's say I want certain lights to stay on until I activate the coil and then those lights are off and a different set of lights come on. You might want to use this logic to make Christmas lights dance to music, for example. This can be extrapolated to work for all kinds of concepts, and that's what makes the relay such a powerful tool. If you're going to use relays, there's a few more things you're going to want to know. Here I've got 2 identical relays except the fact that this one has 2 movable strips. and this one has 4. The number of strips that can switch contacts is referred to as poles. So this is a 2-pole relay, and this is a 4-pole relay. But there's another thing that needs to be added to that, because it starts connected to one contact and then switches to another set of contacts. When you have a pole that switches between contacts, it's called double throw. So this is a double pole, double throw relay. This one is a 4-pole double throw relay. Now, I don't have X-pole single throw relay. Contactors, on the other hand, are usually single throw. So in this case, I've got a 4-pole single throw relay, or technically contactor. The final thing you need to know is that the coils are activated with different voltages depending upon your needs. This one, for example, requires 240 volts to activate, but I have an identical one to this that activates at 24 volts, controlling my dust collector. This one right here is 24 volts. The one I was showing you earlier is 12 volts. You can get them all the way down to 5 volts. It just depends on what your application is. There are a few weird little scenarios though. Let's say I have a Raspberry Pi, which is basically a small computer, and I want to turn on a contactor. But you can't find a contactor that operates at 5 volts. At least I haven't seen one. It doesn't mean they don't exist. You could take a 5-volt relay, which turns on, let's say, a 24-volt circuit, and then that 24-volt circuit activates your contactor. So there's all types of ways to get to the solution that you want. The good thing about relays is that they don't draw a lot of power, and they're also like dirt cheap. So adding a few more of these to your circuit won't have much impact on your overall project. I posted a question a while back on Twitter and Instagram asking you guys if you had any questions about contactors and relays. And one of the things that came up over and over again is, what is the difference between the two and when do you use one versus the other? The short answer is, if you're using something that requires a lot of power, 10 amps and above, or even 5 amps and above, you're going to want to use a contactor. If you need more functionality, you want to get relays with timers and other fancy add-ons, you're looking for a relay. All right, that's enough talk about relays. Let's move on to the relay's cousin, the solenoid. Solenoid or solenoid? I always feel like I'm saying it wrong. You might have noticed that the solenoid has very similar anatomy to a relay. You've got a coil here, the body's made out of iron. What makes the solenoid different really is just its function. It's designed to be able to pull with more force because its primary purpose is to push and pull things, whereas the relay is designed to move contacts. Another reason I want to bring up the solenoid in this particular video is because you often use them together, that is, using the relay and the solenoid. The other day I was trying to impress upon my wife how useful solenoid valves are, and I wanted to think of an example that was useful to her, something she had actually done before. Then I remember she recently built some chairs completely on her own, by the way. I didn't help her. She did an amazing job. But there was a lot of repetitive clamping and screwing. I said, if you had a quick clamping jig, you could take your wood, put it inside your assembly. Maybe we'd have a foot pedal. You put your screws in, and then release it, and now your pieces are screwed together. But then I decided I could do better than just explain it. I could make something that she could actually see and see the practicality of it in real life. So me and my son got together. He built a table for me while I worked on the pneumatics, and we just threw this together in a couple of hours so that I could show her this demo. I'll let you see how she responded. Basic idea, we've got 2 actuators here.
Okay.
And 2 solenoids that move the air between them.
Actuators was moving this part.
Yep.
So it pushes that out, and then solenoids.
You got it. And it's all controlled with a foot switch.
Ooh, foot pedal.
You can step on it.
Wait, right now?
Yeah.
Is it set up?
Yeah.
What happens? Why?
If you want to clamp something, you can do it like that. And hit it again. Then you put 3 screws in and take it off.
Can I touch it first?
Yeah.
Oh, I really is holding it.
Yeah.
Okay, and then.
Yep.
Nice.
Now, of course, we just made this up, but you would normally strap all this down and make it more rigid. Like, there's nothing keeping this down.
So what do you want to film?
I just did.
Jeremy, no. I love you.
Oh, you haven't used it yet.
I haven't. Wait, I get to touch the button.
Yes, you get to touch the button.
Okay. So this button all along controlled the vacuum.
Yes.
How'd you mess with me?
Because it's fun.
Well, I don't know why this is so fun. That's the kids in this shit.
Yes.
Yes. It's just as fun for them.
I just asked my son to come out to the shop to sweep the floor. He hasn't seen this before. Come on in. You're gonna need hearing protection. You're just gonna sweep it all in there. And then turn on the vacuum so you can suck it up.
So the thing that says don't touch the vacuum?
Yeah. Well, you think I like it?
Yeah, cool.
Good.
Much better than putting it into a pan, dumping it into a trash can.
Absolutely. That's why I love it. This is a linear actuator which uses compressed air through these ports to open and close my blast gate. I control the compressed air with the solenoid valve. And in here is where all the action happens. Here we have solenoid valves which direct air to one side or the other of the piston depending upon whether you want the valve to be open or closed. And just like the relay, these all have coils inside of here, and when energized, they move an arm back and forth, which blocks one of the ports and allows the other one to be open. Here we have a contactor, which turns on my dust collector, and here we have a series of relays, which do all the heavy lifting. These guys are what turn on the contactor, as well as activate the appropriate solenoid. You might notice that these relays look a little different from the ones I showed you earlier. That's because these are solid state relays. So while they do the same job, they do it in a very different way. But that's outside of the scope of this video. So maybe we'll cover that in a future episode. I'm gonna turn it on for you real quick so you can see everything light up. The best part of this system is that it's completely automated. When I hit the switch on the various power tools, in this case the table saw, this relay will activate, which will start the whole chain of events, opening the appropriate blast gate and collecting the dust from the right tool. There's one more device I want to show you that uses magnets. Here you can see I've got a PC fan that's not connected to anything, but I've hot glued some permanent magnets onto the fan blades. And the polarity of those magnets alternates north, south, north, south. I've been told that if you can position this just right and get it to bounce and move, you can basically get infinite energy. Oh, almost. Oh, there it is. There it is. Yeah. Except it's a total scam. And this, more than anything else, frustrates me about these free energy videos on YouTube. Want to know how I did it? Well, it starts with this little wireless receiver. This is a wireless receiver which is connected to, guess what? A relay. Let's take a look inside. On the back of this, I hot glued this little plastic dome that I 3D printed. I could make this much smaller, but I'll explain that in just a minute. So right now I'm using a 9-volt battery because this relay requires at least 5 volts to operate. So if I was going to show you this with a relay, I needed to use at least 5 volts. But here's my relay, and right next to it is the little wireless receiver, and this is the button that activates everything to turn it on and off. However, most of the time what these guys use is a reed switch because they are much, much smaller and more deceptive. Let me show you one of those. These little guys are almost microscopic switches. There's a little tab in there that moves or fluxes to connect two wires whenever a magnet is nearby. To show you that, I have taped one to the end of my multimeter, and I'm gonna set this guy to measure continuity. And all that means is when the wires touch, the multimeter beeps. So I'm gonna grab the other end of the reed switch, and you don't hear anything, but when a magnet's nearby, there you go. These little guys are found in burglar systems, which close the circuit on buzzers, to laptops, which when you close the lid, turn the laptop off. It's so simple, so tiny, and so clever. These little guys are super useful, and while many people use them for good reasons, there are also opportunities to use them for bad reasons. Unfortunately, there are entire YouTube channels dedicated to making videos like this, because whenever there's an opportunity to make money, YouTube advertising dollars, there are going to be people trying to scam the system. The recipe is really simple. You take a fantastic story, maybe toss in a little bit of a government cover-up. You take a reed switch, something like this that's very easy to hide inside of this. And then you need a power source that you actually paid for, like a coin cell battery. You put that inside of this device, and bam, you've got a convincing item that'll get millions of views. The only way we're going to get rid of this is we have to stop clicking on those videos. When there's no more money to be made, people will stop doing this. Every engineer on the planet worth anything is trying to find the most efficient way to power their systems. I can promise you there is no government cover-up. If there's a way to get very low cost or free energy, somebody's already exploring it right now. Maybe that's you, but it doesn't look like this. Let's talk about what happened with this switch for a moment. All I really need here is a toggle switch, right? But it's suspiciously low on the wall, it's got a red cover, and it says don't touch. Why bother adding all this stuff? Because if you want somebody to be interested in something, you have to inspire curiosity. I try to do this with every project because I want my kids and family to be passionate about this stuff like I am. I just don't usually record it. It's this desire of mine that makes me so excited to tell you about my sponsor, KiwiCo. KiwiCo makes hands-on projects and toys that teach STEAM concepts. The first time I saw one of these boxes, I was at a friend's house. Our kids were playing together, and this was a big hit with the whole family. Hey kids, Kiwi Crate box is here. All right, come on over to the table. Oh yeah.
There's a lot. Hey, my
Whoa, that was bigger than I expected.
bro.
One of the best things about this is that everything is included in the crate. There's nothing that you need to run to the store for. If it needs batteries, if it needs a screwdriver, it's inside the box. Me personally, I'm impressed with the amount of thought and creativity that goes into each one of these boxes. My kids don't just put together this science project and then they're done with it. They want to play with it. I see them hours later still using it. They have kits for all ages, and it's a family event for us. So I like having a kit for myself to assemble along with the kids at the table. And plus, the linkage on this printing press is pretty incredible. Check that out, man. Isn't that awesome? I should make a video about the printing press. All right, bonus box for Daddy. I think I'm 14 plus. So how you like the lamp?
I like it a lot. It's bigger than I thought it would be, but I'm planning on using the white so it looks more like the Pixar lamp.
Ah, yes. See, what you don't know is she is a hardcore Pixar fan. All of their crate options can be purchased online by going to their online store. They also have a subscription service, which is really nice because all you have to do is select a theme, like doodling or tinkering, and just the right box will show up every month. It also turns out to be a really good opportunity to reduce their screen time a little bit and engage their minds during the summer when they're out of school. So here's the bottom line. If you want awesomeness delivered to your house, you want to inspire your kids, and even support this YouTube channel, you need to go to kiwico.com/Jeremy Fielding. Once you type that in, you'll get 20% off of anything in the store. It doesn't matter if you get a subscription or you buy individual crates or a whole bunch of crates. You're going to get 20% off of your purchase by going to kiwico.com/Jeremy Fielding. No question about it. It's going to be one of the best decisions you make for your family. Thanks for watching.